welcome Yuan.
Okay, so hello everyone. I'm glad so many people are interested in math. It's very surprised, but I'm highly doubt this. So welcome to my talk. It's a journey with about Lean. I will try to introduce Lean, and it is open source proof for the futures of mathematics. So first, let me introduce myself first. My name is Youyuan Yuan. In Chinese, Yuan Youyuan. It's very memorizable. And I'm working in Zscaler as a software engineer, mainly for Rust language. I'm a Rust student with more than 5 years. And I'm also enthusiastic in FAST, and I use NixOS, by the way. I always exploring new technologies. And why I give this talk, because I studied in math in college. Surprise. So let's do it. So what is math? Mathematics is more than just a numbers. It is a language of pattern and logic. So a mathematics is a language. And you may be familiar with arithmetics, but arithmetics is just one chapter in this story. Many focus on the basic operations. And the difference is arithmetics is just the basic alphabet, and the mathematics is the whole story. You can use this story to tell some truths. Math gives us a framework to understand our world and to predict the world. But in mathematics, a truth is just a client. We need to prove it. What's a proof? I believe many of you may not be familiar with this because many people may not continue studying in math in college or graduate. But proof is very important in math. A proof is a step-by-step logical argument showing a statement must be true. It separates the truth from guesswork. It builds the truth in results. And therefore, it can empower science and technologies. So, for example, Pythagorean's theorem, which has been proved over 200 years ago, but now it's still working, right? We learned it at elementary school, and the proof is quite visual. You can just move the rectangles and to see this formula can work. But what is a formal proof? It's something beyond a proof, a handwritten proof. It's a sequence of logical steps verified by the proof assistant, and it's based on a formal logic, for example, based on type theory. Okay. And it can remove the ambiguities and human error. But why it matters? Math relies on rigorous proof. It should be very, very rigorous. But errors still happens in our textbooks, in our journal, and even in existing famous theorems. So we had better use a formal proof to make it 100% verified by computers. Besides, we can unify the jargons. So when I was studying in a college, I suffered from the pain of notation inconsistencies across different courses, across different professors. These notations or the jargons different from person to person, even they are talking the same thing. I believe this not only increase the learning difficulties, at least I feel lots of pain, but also cause a barrier of collaborations. So the motivations is clear. We want reproducibility and we want trust. We want more collaboration. So that's why formal proof matters. Okay, so let me do a quick introduction to Lean. So Lean is intelligence interactive theorem prover plus a function programming language. It's based on dependent type theory and it's open source. You can visit it to see its implementations, and you can extend this. And now it's rapidly growing by communities. And it was developed at Microsoft Research by Leonardo de Moro in the early 2010s. It has been 15 years ago old. And now it's community-driven. But why Lean? Lean provides us a clean and approachable syntax, and the framework is highly extensible. It has powerful tactic framework for proofs, so you can easily write proofs just like human beings. Also, it has a thriving mathematical library, MathLib, and it's still growing. You can see more and more contributors and more people from non-math domains enjoy this. So how to use it? First of all, you need to install the toolchains and the libraries, and then you can edit any files with .lean file extensions with Lean extensions. For example, VS Code provides such kind of extension in Marketplace. You can directly download it. Or it also supports some popular editors like Neowin or Emacs. You can use it with a plugin. Then you can write proof interactively with tactics or some Lean languages. So here is an example. Might be, I hope it's big enough. So we can import some theorems, some libraries, and then here is an example. We try to prove a theorem that the summations of two even numbers is still even. So we will introduce some conditions. M and N are natural numbers, and if we have a HM, a hypothesis that M is even, and another hypothesis N is even, then we can prove M plus N is even. So how we prove it? We can use by to introduce some descriptions of this proof, and then we prove it sequentially. Okay, so let me do a live coding. I believe show you some code can make you more familiar with Lean. Make it larger, okay. Okay, so this is a quick example for Lean. How does it work? First, you can import some library, and a quick example could be done by, for example, we want to show 1 plus 1 equals to 2. Everybody knows this. But in Lean, we can prove it by a tactic, a reflexivity tactics, which is just equal equations. And then we can also prove it by, for example, if our question is there any natural number satisfying 4 equals to 2 times n? Then we can construct a concrete example for this to show it. So we can use 2. And if we plug 2 into n, then problem solved. Very easy. Okay? And then we can also mark some theories, leave all the readers' homeworks, like famous less theorems. Yeah. It has been exist and unsolved for more than 500 years. The claim is like this. For all integers n greater than 2, there's no ABCs in natural numbers satisfying A a to n plus b to n equals to c to n. Yeah. But anyway, we won't prove it at here. So we can solve it by, sorry, I have no idea. Yeah. So it's quite useful and extensible. And here we can prove, we can have a more closer look on how link works. Like if we give an example and the problem is A and B implies B and A. It's just an exchange of two propositions. And then how to prove it? It's just, if we already know A and B is correct, then we just swap it and return it. So in Lean is to construct a concrete instance for these propositions, or construct a term for this type in type theory language. And also we can use it in a tactic mode. We will need to use a by. And by introduce a edge, which is A and B. Then we can return it that is actually is exactly h dot right and h dot left. Just swap the orders, then done. Okay. Okay, and then this one may be a little bit complicated. So please bear with me. We want to show it step by step, just like we writing on the papers. For example, if we have example f and g's are real functions, you will map real numbers to a real domain, and we want to construct a property. It's called even functions. An even function can be constructed by definitions. For functions, for real functions, for any x in its domains, we call this function is even if f minus x equals fx. Yeah. So it's quite easy. So here we want to prove that an even function, a summation of two even functions is still an even function. And sorry. Yeah, make it better. Okay. So I want to demonstrate that Lean can also prove step by step by introduce a calc, this tactic. So first, we want to prove f plus g equals f plus g of minus x finally equals to f plus g of x. So that f plus g is an even function. If you see the right-hand side here, we can see the goal of this is this one. We have some hypotheses. F is an even function, and g is also an even function. And our goal is to show f plus g, these summation of these functions, these two functions, has these properties of minus x equals to a positive x. Okay, so we can calculate it step by step by first we can decompose it by reflexivity, and then we can do the second step that because we know f is an even function and g is an even function, so we can rewrite it. As you can see here, rewrite it. And done. So Lean can be proved by, first we can prove by construct a function, a concrete type for this, or we can use tactic mode and prove it step by step, just like we solve a math on the paper. Yeah. Okay, and then let's take a more closer look on the Lean proving systems. First, we can define properties, which is called non-decreasing. A function is called non-decreasing if for any x2s is greater than x1, f of x2s will be greater than fx1. So these functions will decreasing or be equal, okay? And it has two ways to prove it. One is forward logics. Just like I said, we can construct it by a very complicated format. Otherwise, we can use a backward logic. A backward logic might be close to what human beings think. For example, first we can introduce a hypothesis so that we have some tools to prove it, like f is non-decreasing, g is non-decreasing, and x1 and x2 are in a real numbers set. Okay, and then we apply it. We apply the hypothesis. We apply a lemma, so that we change the goal from this one. This one is previously our goal, and then we change it to this one, because we already know that f is non-decreasing. So we just simplify the goal and prove it step by step. Okay, and then we can further simplify it, because we know f is non-decreasing. Okay, so we begin from this to this, because g is non-decreasing and then f is non-decreasing, and done. Because we already know that one of our hypotheses is x1 is less or equal to x2. So we prove it. Okay, so it's quite easy. And in a more complicated case is we can construct it cases by matching the hypothesis with some concrete example. For example, to show the summation of two even numbers is still even, we need to show, we need to construct numbers. For example, the definition of x is even, it means there is a y such that x equals to 2 times of y. So there must be an y. Okay, so we can use our cases on this hypothesis to construct a concrete, for example, A, and with this property HA, such that m equals to 2 times of A, which means m is even. And we do the same things on the Hn, okay? So that after doing this, our goal is we want to show m plus n is even. The summation of two even number is even. We want to show it. And we already know that we have m equals to a plus a and n equals to b plus b. Then we use it. A plus b is our solutions to this. Then we apply it and we rewrite it and done. Finally, the latest one, the last one ring is some basics operations that we usually use in our elementary math, but it's just a high level notions in math. Yeah. Okay. So that is a glimpse of how does Lean works and how people can interact with a Lean prover. Yeah. Okay, so let's go back to our slide. So let's talk about the foundations of Lean. Basically, Lean relies on a constructive logic. A constructive logic is a system of logic where a proof is a construction, just like we showed in our example. And there's no truth without a witness. So you must construct it. And in Lean, propositions are types via some fancy terms, Curry-Howard correspondences. I will explain this later. And to proving some things, it means constructing the value of a certain type. So for example, here, to show a theorem, we need to construct its instance. In computer language or in type theory, we need to construct a term of this type. Okay? And what is a Curry-Howard correspondency? Well, it's a deep and beautiful connection between logic and programming. In terms of logic, a proposition P is a type P in type theory. And a proof of P is just one point inside this P. It's a term of type P. So for example, P and Q, which is a claim, which is a propositions, is just a product type in the type theorem. And implications like P, if P, then Q, then it can map to a function type in type theorem. P maps to Q. Or for all x, there is Px. For all x, there is some numbers greater than 0, something like this, which is also a proposition. It just can map to a dependent function type. So with these theorems, with these correspondences, we can map in a logic into a programming. And I will quickly go through a dependent type theorem, which is the backbone of Lean. Why we use type theorem? Because using a type theorem, we can check the correctness of a proof. A type theorem is a foundation of mathematics and computations, which every term, just like I said, is it has a type. It belongs to one single type. And if it belongs to there's every term belongs to one type. And between two types, there is a relationship we can prove they are equivalent. Yeah. And you prove things by constructing terms to these concrete types. Yeah. And why we call it dependent? Like if we want to construct a vector space, then it's not a simple vector space. We need to configure it with it is a vector space spanning on natural numbers with dimension 3, something like this. So a dependent type means it can be dependent on some values. This is very similar to constant generics in Rust, but it has no limitations on constant generic. Yeah, limitation on constant. Okay. So this is a core part of the proof. Constructive logics can be mapped to a computable logic. Because a proof can be considered as programs. Every proof in constructive logic is to construct functions or a data that you can evaluate it. If it is successful, it means this proof gonna work. And this makes a constructive proof more aligned with computations. And you can note that you're not just checking the logic, you're building a program that can guarantee the correctness by their type. So it's just like you write a program and you let the compiler to check its correctness. And in the end, the proofs are irrelevant if they all construct an instance to these propositions. So prop is a type of all propositions, and a proposition P is one type in prop. And this type you can construct a theorem, you can construct a term to prove it. For example, we have a theorem F, and it has some properties, and it belongs to this P. And then you can prove it by constructing H, which is a proof. If you have other way to prove it, like an H1 and H2 or H3, those are equivalent to this proof. Okay, and there's one major difference between the constructive logics and the classical one. We don't have the law of the excluded middle. For example, classically we have either this proposition is true or is non-true, which is called the axiom of law of excluded middles. But it's not always true in Lean. Also, we don't have non-P means P is correct. Okay, and also we don't have a free existence. So in constructive logics, we need to construct it. So like there's no truth without witness. But you still can use it if you extend the Lin's axioms by open a classical library. Then you can prove something like by contradictions. It's also permissible, but you will live in the realm of a purely constructive logic. Yeah, there's a trade-off. Okay, so this is the central of this part. In a nutshell, constructive logic is to prove something you must construct it. And it depends on two essential foundations. One is Curry-Howard correspondences. Proof can be considered as programs, and propositions are just types. And it depends on dependent type theory so that we can extend our system to very high dimensions and very extensible dimensions. Yeah. Okay. So I will summarize the recent development on Lin's ecosystems. First of all is MathLib4. It is a huge modern mathematics libraries written in Lin4. It has been ported from Lin3 to Lin4 in 2023. It has now more than 1.5 million lines and over 660 contributors, and still rapidly growing. It covers all core areas of elementary mathematics, but also modern mathematics, algebra, topology, analysis, logics, and more. It's fast and scalable, and welcome for new contributors. And if you want to learn Lin, I will highly recommend you to play with this. Learn Lin by solving a puzzle, the natural number games. You can click it, and it's just like you can follow the tips step by step and solve some basic puzzles like why x plus y equals to y plus x, or why x plus y plus z equals to x plus y plus z, depends on the orders. Yeah. Okay, and regarding learning resources, we have a glimpse of Lin. If you just want to learn Lin in a few hours, you can try with this. And if you want to go further, if you are highly interested in math, I will recommend you to test mathematics in Lin. Also, we have several conferences in the past, which is called Lin for the Curious Mathematicians. You can search for this and to see our past event. And if you want to see some videos, Lin Provers communities, it has official YouTube channels. Furthermore, you can use a search engine to search the tools, the tactics, or the theorems with the keywords or some type hints. Yeah. And don't forget to join the Zulip. There's the channel. There are lots of people there, and everybody are interested in exchange ideas and contribute to Lin. Okay. That's my last 3 slides. I will summarize the histories of Lin. In the past, there is a advanced research called liquid tensor experiments, once led by Peters and Kevin, and it has been completed in 2021. It was a milestone for Lin in cutting-edge research. It's not an elementary math. It's a very cutting-edge research. So Schwartz, who won the field medals in 2018, he was unsure about one of his latest results in analytic geometries. And the work was thought that it would take years to complete. But finally, it just took a few months to complete with the help of communities and the prover systems. Surprise. And the impact is it proved that these could be used on new math, not just classic elementary ones. And we have the results that MathLib with rich for algebraic and topological foundations. And what is ongoing? There's a group of researchers formalizing the famous Lesch theorem. So just like I said, the statement is there's no positive integers x, y, z solve x to n plus y to n equals to z to n for any n greater than 2. It has been stated by Fermi, and he just said this is corrected, and I already proved it, but there's no sufficient space to write it down. And it takes more than almost more than 300 years to prove it rigorously. It was solved by Wells in 1995. But now we want to more formalize it. It's led by Kevin since 2024. The goal is clear. We want to fully formalize his original proof in Lean. It's not an easy job. We need the concrete foundations for the underlying theories. And the significance is it will be the largest formal mass proof project ever. It's publicly open, so if you are interested in it, please have a look. Okay, so what is the futures of Lean? It will open a new era of mathematics, I believe. Formal proof, it will bring us global collaborations. We can verify our textbooks, and we can check the papers by machines. Math will be reproducible digital knowledge open to everybody. And Lean4 is not just for math. It can be used on compilers for softwares, and also checking the system for like mechanical systems. We can verify its safety. And the most exciting is we can introduce AI into this. So DeepMind from Google's, they are currently working on alpha proof to show Lean or the AI proofers can solve math Olympiad questions. And also there is Lean Dojos. It maps Lean's data, the Lean proof to a concrete data set, so that we can train some large language model to learn it and then to help people to prove something, even we don't have no ideas. Thank you. So this is the end of my talk. Any questions?
Thank you for your talk. Happy to see a bit of math in a very computer science-oriented conference. I was wondering if you can maybe give your opinion about the difference between different theorem provers, because you've talked about Lean, but I think there is at least ROC, or I think it was called COG before, that exists. And do you think Lean maybe is better, or maybe the community is larger, or yeah, what do you think that there are different provers?
Okay, this is a good question. So I believe there's lots of questions about maybe comparisons with other existing provers, right? So first of all, it's highly different from Isabelle's, which use classical logic. And Lean is highly close to COQ, COQ. And they both use a dependent type, and they both use constructive logic. But Lean has is somehow close to math, and COQ is for verification, general verifications. And for Lean, it's try to make proving math propositions as easy as it can, and let everybody to extend this. So there is important notions in Lean. It's called domain-specific language. You can implement your tactics like buy some things. Maybe you have some domain-ologies and you want to customize it. And I forgot to mention this. Lean has been very mature. most of the Lean code is written in Lean itself. Just part of it written in C and C++. Did I answer your questions?
Yes, yes, thank you.
Yeah. Any other questions?
I have a question about how did you apply the Lean like tool just put a system in your work item, like because in your slide I always see the example about mathematical content. Because I'm a hardware design engineer, so I don't you have something idea about how to use Lean to do hardware design or some system design?
Okay, for design something, I think first Lean is not creative for creations yet. We need to use some LM model to do it. Lean is to prove something you claim. So if you are focused on system design, then you can formalize your claim in a propositions. First, you can construct it by define some properties, and then you try to prove it by, if I have some hypothesis, then I try to use Lean to show its correctness. So I believe the very typical example is we want to show there's no deadlock in a concurrent system. Okay, so we can define the order we receive the data and the order we write the data. And we can define the order with some timestamp. Okay, and then maybe we are curious about some program that we receive and reply. And I construct it in a concrete propositions and try to write its proof according to my previous definitions. Maybe these definitions only works on your systems, but you need to construct it. You need to formalize it. Yeah.
Okay, thank you.
Sorry, we are a little bit over time, so I'm gonna cut it now. And then if you guys have any questions, please contact the speakers. You can email him, and then every slide and the contact information we will also upload online. And we're gonna, without any break, we're gonna get into the next talk. So every field has its own buzzword. Thanks to the speakers first.